Welcome to the sixth talk in our higher categories reading seminar. Today's speaker is Logan from UCLA. And okay, Logan, take it away.
All right, so last time when we were talking about infinity cosmoi, we defined an infinity cosmos K as a certain kind of simplicially enriched category, which is enriched over quasi-categories and has certain simplicial limits. And then we also defined isofibrations, equivalences, and we showed that equivalences in an infinity cosmos K are the same as a two-categorical notion of equivalences in the homotopy 2 category of K, which we got by truncating the Hom quasi-categories to, or rather taking their homotopy category to make them into regular categories, so we get a strict categorically enriched category. All right, so today we're going to talk about junctions, first of all. So let's start with definition. So in an infinity cosmos K and a junction, F is left adjoint to U, F maps A to B, and U maps B to A, is the data of these two functors. Along with natural transformations in the homotopy 2 category. Eta maps the identity of B to, should be identity of A, UF, and epsilon maps FU to the identity of B, such that we have these equalities. Sorry. I should probably be drawing this the other way. Okay, sorry, I'm butchering this. Let me draw this like this. This equality and these two are called the triangle equalities. So what these mean is to read these diagrams, you're just going to look at these as underlying graphs, and you're going to look for the string of edges which has no two morphism ending at them. And this is going to be your source. And similarly, you're going to look for the string of edges that has no two morphism starting from any part of it, and that's going to be your target. So this top one is just telling you that epsilon f of f eta is equal to the identity of F. And the bottom one is telling you that U epsilon of eta U is equal to the identity of U. So these are just your normal triangle equalities that you have from ordinary category theory. And in this case, say F is left adjoint to U. And write A to F left adjoint to U from B. That is the way I put them, right? Yeah. Okay. So this is how you can define adjunctions for infinity categories, and it's actually how Joyal originally defined the adjunctions for quasi-categories using this sort of system. And now we get a bunch of nice facts from it. Since this is just general definition for any two category, and all this data is preserved by any two functor preserves adjunctions. In particular, fun x dash dash to the j for j a simplicial set, or an infinity category if you're in a Cartesian closed infinity cosmos. And taking, for instance, products, all preserve adjunctions, because these are all different two functors, or at least they descend to two functors on the homotopy two categories. All right, and now with this in hand, we can prove certain facts about adjunctions. We can prove proposition, adjunctions compose. So say we have a, I'm going to reverse F and U now, because I just want it to look like this. Suppose we have adjunctions like this, and F prime, U prime, with unit eta maps the identity of B to UF, epsilon maps FU to the identity of A, eta prime is going to map the identity of C to U prime F prime, and epsilon prime is going to map F prime U prime to the identity of B. Then we claim that F prime is left adjoint to U prime U. All right, so now let's prove this fact. So with these natural transformations in hand, we're going to define a new natural transformation eta prime prime is going to map the identity of C to U prime U F F prime. And we're going to define this by, start with C here, the identity over to C. Now we're going to go down here by F prime. We're going to have here B, and we have equals to B. Over here we can go back up at U prime, and we have a morphism here, which we called eta prime. And then we have over here to A, and back up by U, and we have what we called eta. So we're going to define this as eta prime. And we're also going to define eta prime prime. Epsilon prime prime from the identity on A to FF prime U, sorry, it should be the other way around. FF prime U to the identity on A. And we're going to define this one as just composing the co-units similarly. So we have A going up to B by U, coming back down to A. And we have this epsilon here. And we also had U prime and F prime, along with an epsilon prime. And now we're just going to check the pacing diagrams that these actually do form the triangle equalities. So let's just do one of them. So we have C down to B.
Excuse me. Yeah.
Yep.
So yeah, so I just wanted to ask, like, is there a way you can shrink it, or shrink it? I mean, so that you can see more of your slides. Is there a way? Yeah, I think that's.
Let's see.
I mean,
I don't know.
so in that way, I mean, you can see more stuff. Or maybe you can just like pause for a second and then.
All right, yeah. I think that's what I'm gonna do because I don't know how to shrink it.
Thanks.
All right. These are the diagrams we're gonna be using. So we're just gonna put these down here next to each other. So we're gonna have down here by F prime, and we're gonna go by F, and we're gonna go back up by U, and then U prime, and then back down again by F prime and F. All right, so the way we drew our morphisms, we had this one was eta prime, and here we have eta, here we have epsilon prime, and here we have epsilon. Just these here. And now, using a fact about two categories that these end up working out, this bottom one is equal to, so this bottom one, I mean this here, this is equal to B to F equals F A. And the top one is just C by F prime equals F prime to B. And this is just equal to C, F, F prime, F, F prime with an equality between them to A. So this is one of our triangle equalities. The other one you can check very similarly. All right. So now we can prove another proposition. Equivalence and variance of adjunctions. Or not quite equivalence and variance yet, but rather just uniqueness. Equivalence and variance comes later. So uniqueness of adjunctions. So let F be left adjoint to U, and F prime also be left adjoint to U. Then F is isomorphic to F prime, as functors. And conversely, if F is isomorphic to F prime, then F prime, sorry, and F is left adjoint to U, F prime is left adjoint to U. All right, so for the first claim here, suppose we have F is left adjoint to U and F prime is left adjoint to U, where F, F prime are going to map B to A, and U is going to map A to B. And say that we have respective units and co-units, eta, epsilon eta for F left adjoint to U, co-unit unit, and then epsilon prime, eta prime. And we can form the morphism from F to F prime by looking at B goes down by F to A. We can take this up by U back to B. And then here we're going to take this back down to F prime to A. And here we're going to have, this is going to be eta, we said, and this one is going to be epsilon prime. So this gives a morphism from F to F prime. And if we want to see this is an isomorphism, we just append a similar diagram on the other side. So we have eta, A, U, F prime, back to A. We're going to have here epsilon prime, and we're just going to chalk on going back up by U again. And this time we're going to go down by eta prime, and then we're going to go back down to F by to A, and down here by epsilon. And in here, these are going to cancel because of the triangle equality. So this is just going to be the identity on U, and then we can cancel the total thing, and we're going to get the identity on F. And similarly, if you flip the sides around. And conversely, if F is isomorphic to F prime, then just add in the isomorphism on either the unit or the co-unit. So in this case, your new unit might be B equals B F prime let me do it this way, actually. So you're gonna have eta, and then you're gonna have some isomorphism here. And your co-unit, that's down here, equals A. You have going up by U to B, and then you can go over here by F and F prime, and here you just do the inverse isomorphism that you had there. And epsilon. And then when you concatenate these two together, the isomorphisms are going to cancel, and you're going to be left with your triangle equalities. That is left to check. All right. Next, we have a theorem. This is the minimal data for an adjunction. So if we have F maps B to A, U maps A to B, eta maps the identity on B to UF, and epsilon maps FU to the identity on A, such that the natural transformations we get from the triangle diagrams. So for instance, A going up to U to B equals B, and going back down by F to A. And then here we have epsilon, going back up by U, here we have eta. Are isomorphisms. Then F is left to join to U. And in fact, we can let eta be the unit or epsilon be the co-unit just by changing the other one. This is 2.1.1, sorry, 2.1.11 in elements. It's a bit of a diagram chase, so I don't want to go into it for the sake of time, but it basically just involves taking one of these isomorphisms, correcting either the unit or the co-unit by it, and then showing that you get one of the triangle equalities for free, and the other one you get from a cancellation, and using the fact that one of these morphisms is an isomorphism, so it's going to be able to be canceled. And as a result of this, we get equivalence and variance of adjunctions. Actually, we can get that as a corollary or something else. We get that corollary equivalences are adjoint equivalences. So you can upgrade any equivalence to an adjoint equivalence. So what an adjoint equivalence means is that we have A to B here. We have this adjunction such that eta and epsilon, the unit and co-unit, are natural isomorphisms. So it's an equivalence just with these unit and co-unit respectively, but they also satisfy the triangle equality. And the proof is that just take any equivalence, F with inverse equivalence U, then take natural isomorphisms, eta and epsilon witnessing this, and apply the theorem. Because both of these would be invertible, their composite would be as well. All right. So with this, we get a corollary of equivalence and variance of injunctions. If A is equivalent to A prime, B is equivalent to B prime, and we have F is left adjoint to U, F maps B to A, U maps A to B, then if F prime, U prime are the corresponding functors under the equivalence, then F prime is left adjoint to U prime. And the proof is upgrade both equivalences to adjoint equivalences. And use the fact that adjunctions compose. All right, so that's about all we have for adjunctions right now. So now it's on to limits and colimits. Valued in infinity categories. All right. So what should a limiting colimit look like? Well, if you think more classically, what we have is, for instance, in the very basic case, let's look at like a terminal object. So we have a terminal infinity category, and we have a unique map from A to it. So an initial object in A is going to look like a left adjoint to this. And a terminal object in A is going to look like a right adjoint. So this is going to give you terminal object, initial. And this is precisely what we use as a definition in Infinity Cosmos, but this is a very special case. It's only like two things. So recall that if, we're going to define limits of diagrams. We want J to be either a simplicial set, and then we're using simplicial cotensors, or an infinity category if the ambient infinity cosmos K is Cartesian closed. So this is just saying that we can form a category of diagrams A to the J. All right, so if A has all J-shaped limits, then the diagonal functor, this is an ordinary category theory, and J is a category for talking about ordinary category theory, but just pretend it's the same. Because I mean, you can just take the category in the special set anyway, the homotopy category. The diagonal functor, A to A to the J, has a right adjoint. Similarly with colimits and left adjoints. So by definition, an infinity category A has all J-shaped limits if the diagonal functor a to the j, this is going to be induced by j to the terminal either infinity category or simplicial set, and then taking simplicial cotensors or internal homs, then the diagonal functor admits a right adjoint. Lim maps a to the j to a. And then we can talk about diagrams in here, say as generalized elements, or rather as elements from one, which are maps from one, or generalized elements where we can take some other infinity category D and look at the map here. Then we can look at the limit of the diagrams that this generalized element gets. But this is only if you have all limits, and dually if you have all colimits. This doesn't cover a lot of interesting cases that we would want where we don't necessarily require that something has all limits. So how do we fix this? So we're going to have something that is sort of dual to Kahn extensions. It's called absolute lifting diagrams. All right, so given a diagram, B going down, say, by G to A, here we're going to have C by F. We can look at L here and some natural transformation rho going up here. We say that L rho is an absolute left lifting of F through G if for all X and diagrams of the form X going down by C to C, going over here to B. Here we're going to have going back off to A, just ordinary things before. And we're going to have some natural transformation here, chi. There is a unique zeta. It's kind of hard for me to draw, so let's just say tau. Tau, making the diagram, or making the above equality hold, let's say. So this is some sort of dual to Kahn extension. So whenever we have a natural transformation from this here to some other infinity category, we can just lift it through this row. So in particular, here's some useful facts about it. If L comma rho is an absolute left lifting, also dually we have absolute right liftings. Or dual by taking all of these natural transformations going down instead of up. So from GL down to F. All right, so if L rho is an absolute left lifting diagram, and R maps R to C is any functor, then LR rho R is an absolute left lifting diagram. So let's draw this out. C goes over by F to A. You're going to have G down by F. We're going to have up by L. We're going to have this row. And then we said we had R over here. And why is this? Well, take any X over to R into C, F, A, over to B, down by G, and some chi. Well, this is equal to X goes to R and then down by R to C. Then here we're going to go up by L, over to B, down by G to A, up by rho, and then there's going to be unique tau here. And then this is tau is the same as X goes down by R, and then we're going to go up by LR to B. We're going to go up here by rho R, G, A, F, B, and then we go by this tau. This makes us all commute, and you can check that anything else that makes this here commute, you can expand out your definitions and get that it has to be unique and equal to this tau up here, just since it would make this diagram commute. So that gives the claim. All right. Now we have a lemma. If I check my notes because I'm not going to remember which way the unit and co-unit should be otherwise. All right. Okay. So if we have F maps, actually let's just do U maps A to B, then F is left adjoint to U with unit eta if and only if B is equal to B. We have up here A going down by U to it. And we can take this map up and go down, go up by eta, is an absolute left lifting. And dually, you have that going down by F to A with U right adjoint if and only if the co-unit is an absolute right lifting. All right, to prove this first one, suppose first that F is left adjoint to U with unit eta, and take any diagram over this. So we have B equals B. Here we have A going down by U. And we're going to have some X over here by A, down here by B, and some morphism chi here. Well, we can take this diagram and we can go ahead and we can paste with going over here by F to A. We're going to have this equality, and we're going to have the co-unit here. And we can see that if we do this, then after we take this diagram here with the unit, then since this part here by the triangle equality is just equal to the identity, we're going to have that this is equal to X to A down by U to B, down by B to B, and down by chi. So this tells us that this tells us existence, because we can just take, if we were to erase this part of the diagram, let me just circle it in red. If we were to just chop off this part, then this up here gives us a morphism up this way. And this down here is precisely this part here with eta. So we can just add this on, and this is going to give us existence of something up here. This chi is going the wrong way. And to show uniqueness, all you have to do is suppose we have x going down by b to b, a to a, f here, some morphism zeta, let's say. Here we're going to have eta, u to b, this here. Well, you just add this f back on. You do this epsilon here, and then this part here is equal to IDF. So this part here is equal to, in total, zeta. But if we check, we saw that that was equal to chi, and we defined this as doing it with chi. So we see that zeta is actually equal to this diagram here. And that proves uniqueness. And conversely, if this is an absolute absolute left lifting, then we see that we can apply this with A is equal to U and is equal to A over here, along with the identity natural transformation on U. And then we're going to see that this is equal to a unique epsilon up here. This diagram here, which is automatically one of our triangle equalities. And in order to get the other one, we just have to do B down by F to B, sorry, F to A, up by U to B, back down by F to A again. We're gonna have to do this equality here, and then eta epsilon. And let me draw this the other way, actually. Draw this up so that it looks better for what we have. Sorry. And we're just going to add this part down here, eta. Now we already know that this part in red is equal to the identity on U from right here. And we know that this part of the diagram in blue is unique for lifting whatever this diagram here is. But since this diagram here is equal to B just going up by F to A, then down by U is equal to B and eta, then we can look at this diagram over it and we see that this here has to be the identity on F, which is giving us the other triangle equality. So therefore we have the zeta of an adjunction. All right, well, what does this mean? So if A has colimits, then A to the J is equal to A to the J. Here we have A, this is our diagonal functor. And we're going to put the left adjoint, which is colimit, along with the unit, is an absolute left lifting. And by our lemma earlier, this tells us that if we have any D going off by D to A to the J, then colim composed with D up to A, down by delta, along with A to D, is an absolute left lifting. In particular, if you're just picking out one diagram, so you just have D is equal to 1, then this is how you would pick out the colimit of a particular diagram that you're thinking of. So this motivates the following definition. Given a generalized element in the category of J-shaped diagrams, so some functor from D to this cotensor here, or internal hom, a to the j. A colimit of D is an absolute left lifting D goes over by D to a to the j through the diagonal functor. Note that this definition does not require A to have all colimits. It doesn't even have to have any particular ones. You just need to have whatever ones are indexed by D of shape J. So in particular, if we had some other element of D, we can still test and get this colimit here, so we can still pick out one object diagrams. And this lets us do a little bit more in general, because it's not always the case that just doing one element here is going to give you all of the different possible colimits. You might have other stuff that conflicts. And dually, an absolute right lifting of D through delta is a limit of D. Okay. So you can show that these absolute right liftings are going to be equivalent to variance. And for instance, we can talk about what preserves limits. So lemma, right adjoints. Actually, let me do, since we've been talking about colimits more, let me just do left adjoints preserve colimits. And the dual statement follows. All right. So if we have a left adjoint, F maps B to A, F is left adjoint to U, and some absolute right lifting, so D through D here to A to the J, up to A, down by the diagonal. So we have the colimit of D. Then we want to show that when we compose with the functor from A to B, which is, I'm doing this the wrong way, this should be from B, sorry. From B to A, because we want the left adjoints, A to the J. Here we're gonna have our diagonal functor from B, colimit, our eta, we can go over here by F to A and then down by the diagonal. We want to show that this is an absolute left lifting. To do this, we're going to use the following fact. If we have a diagram let me keep my notation consistent with what I was doing earlier. It looks like this. Then sigma, I guess. If rho comma L is an absolute left lifting, or L comma rho, I think is more consistent with the notation. Of F through G, then R comma rho, or sigma, I'm butchering this, is an absolute left lifting of L through H if and only if R comma sigma, let's see, go in here once. Sigma, or sorry, G sigma of rho is an absolute left lifting of F through GH. This isn't too hard to prove. It's just balancing universal properties. And using this fact, what we do is we note that this diagram here is going to be the same as if we append. So what does that look like? All right, yep. This here. Then we can also look at tossing on our U, and for this adjunction, F is left joint to U, I'm going to use delta as unit, because I already used eta, and epsilon is the co-unit. So here we're going to have delta to the J. So since this down here is an absolute left lifting, then the diagram we want is if and only if this whole diagram is. Now, in order to see this whole diagram is, we're going to use naturality of the simplicial cotensor, and we're going to turn this diagram into looking like D up to colim D to B, and we're going to have equals to B here, A up here, going up by F, down by U, down by delta. Then we can take diagonals to B to the J and have D down here. Or rather, it's better to do. That's actually fine. And here we have eta. This should be going the other way. So this is the same as that diagram there. And this down here, we already said by hypothesis was an absolute left lifting. And up here, since F is left joint to U, implies it's an absolute left lifting. So the whole diagram is and we're done. Any questions so far? Okay, we only have a few minutes left, so I don't want to start anything too new. So let's just talk about basic kinds of limits. If J is some coproduct of the terminal element 1, then a limit of shape J is a product, and dually a colimit of shape J is a coproduct. In particular, we can see just by balancing the universal properties under this bifunctor that A to the coproduct 1 is equal to say we're taking the coproduct along some set I, product I of A. And since taking the homotopy category, in the case of quasi-categories, it's clear what to do. In the case of general infinity categories, you're taking the homotopy category of the quasi-category of functors from the terminal element A. And doing this preserves two categorical products. The adjunction, if A has all products, A to product IA, descends to an adjunction on homotopy categories homotopy category of A to product the homotopy category of A. This is since homotopy category commutes with products. This is not true of general A to the J. We get this adjunction here, which tells us that the homotopy category A has products and that the products agree with what they would in A. In general, H A to the J is not equal to H A to the J. So colimits don't necessarily define colimits in the homotopy category. But it's rather some sort of a weaker assumption. All right, I think I'm going to stop here because I don't have too much more to do if there's any questions.
Let's thank Logan then. So maybe I can stop the recording.
Yep.